Good morning. I hope you're doing well. Apologies for starting 1 minute late. I had a bit of a mad scramble to get everything ready and up and running, but we got there. I haven't had a chance. Normally I run through my slides one final time just to make sure that everything's good, but unfortunately I did not have time this morning, so hopefully everything is in a sensible order. But yeah, this week overall, big picture view was, on some days, Tuesday in particular, was a very, very, very frustrating day. I was not loving it. It was pretty draining, but thankfully Tuesday ended as all days do, and there were, I don't know, brighter horizons on Wednesday and yesterday. So we've come back around and everything is good again. But yeah, it's frustrating sometimes, and obviously I'll explain how it was frustrating as we progress through today. What did I just change? All right, let's go to here. Cool. Yes, so Juggerwatt is temporarily out of commission, which, I don't know, sounds like it could be a bad thing, but it's honestly not too bad. Let me actually just show you what Juggerwatt's looking like right now. He's in a bit of a sorry state. I say he, I don't know, it. I feel is more appropriate maybe. But yes, we've had to take out all of the legs, and now I am going through what should be a straightforward process, but it's turned out to be a whole thing of measuring the legs. But we'll get there when we get there. There's one thing that I want to go through first though, which is something that I want to make a segment on these streams, on weeks when it's relevant. It's not relevant for every week, but there have been a few times where I've been thinking of kind of like cool things that are tangentially related to Juggerwatt, but are not actually like the core project. And I don't know, I want to have like a way to share that with you all in a fun way, so that way there's like something, I don't know, light and easy to look forward to in the streams. Again, it won't be every week, but whenever it is, I want to add this in. But I need to think of a better name for this segment. Right now it's just fun tangential thought, because as I said, I was running out of time and I wrote this slide about 5 minutes ago. So yes. But this week's fun tangential thought, name TBC, is related to Ball Butler. So obviously the main project here is to make Juggerwatt a juggling robot, or like a series of robots, a troupe of juggling robots. But a side project that I am very, very keen on is to make a Ball Butler, which would be a robot that I can take with me when I am juggling myself, and whenever I drop balls, it can somehow return the balls to me so that I don't need to bend over and pick them up, because I hate having to do that. It drives me mad. So, one issue that I have with Ball Butler right now, at least, is that it needs to be able to get to the park where I juggle. Kind of annoyingly, the best place that I have found to juggle is a park kind of near my place. It's like a 10-minute walk maybe, which is like, it's a bit far. But obviously it'd be great if I just had like a room in my house, but, well, unfortunately I don't. But yes, so Ball Butler needs to be able to get to the park with me, and I don't want to carry it. If it weighs more than like a kilo, I don't want to carry it, which functionally means I'm not going to carry it, because there's no way this thing is going to weigh less than a kilo. If something can like pick up balls arbitrarily from the ground and return them to me, that's going to weigh more than a kilo. So it needs to be able to get to the park by itself. Once it's there, it also needs to be able to move around to collect the dropped balls, because like that's its whole purpose. And so I was thinking, I've considered this for a bit, and like my go-to thought the whole time up until now is to have like a remote control car sort of thing that can drive around, but then somehow give it like omnidirectional wheels that it can drive around, like so it can just move sideways rather than having to do like 15-point turns to get the ball that's right next to it. But I don't know, I feel like that'd be tricky with grass, like omnidirectional wheels with like the little tubular wheels. I don't think that would work very well on grass. And this whole thing is, like, the car idea it's never really sat right with me. It's not quite what I want, I think. So I was thinking about it this week, and I'm like, oh, okay, what else is there? Maybe, we could use a robot dog, because they're not that expensive nowadays. And so I was looking at this one in particular, the, what is it, Unitree Go 2, get out of here, health thing. And these look pretty cool, and they're not like that expensive. And I'm wondering if I'm gonna message them and see if they are interested in sponsoring this project, because I feel like this would be a pretty cool project. Like I've never seen these actually. I need to do a bit more reading into these, but I've never seen any like project where people have actually used these for a real thing. That's not just like, hey, look, it can do, I don't know, handstands or whatever, like these things. Like, yeah. So I don't know. It would be interesting if they sponsored the project. Then I would be very, very, very keen to use this. And like it can run with you, it can just walk itself to the park. I can like put my balls on it, like my juggling balls on its back, so it can just like carry all of my stuff with me. I can give it like a camera so that it can like see me a bit better. Like, oh, it'd be so cool. So I'm just kind of, yeah, thinking about this a fair bit this week. This is kind of what's pulled me through my dark times on Tuesday. But yeah, that's my fun tangential thought for this week. I think that would just be so cool. It'd be pretty good. But of course, then there's the question of like, okay, it's the dog. Like that's just like the platform that the thing that picks up the balls and returns the balls to me is on top of, and my intention will be to put something on top of it. And they do sell an arm as well that goes with it. They've got examples of like it opening doors and like pouring a wine glass and that sort of stuff. But that arm is like 5 times the price of the dog. So I'm skeptical that I would be able to get that. But I feel pretty good that I'll be able to build something that goes on top of the dog that can then pick up the balls and return them to me. Which would be so cool. But anyway, yes, that's the fun tangential thought for this week. On to the actual content for this week. After I have a drink of water. So, last week we had a lot of talking about optimizing the robot's geometry so that the virtual geometry on the computer is identical to the actual physical geometry of the robot. And this is very important because it will, without the virtual geometry being identical to the physical robot geometry, it's going to be very hard, and it is very hard to get the robot to move to where I want it to move to. So we want these to be like as spot on as possible. And yeah, there was a lot going on there. There was probably too much going on. And yes, so we are currently, right now, I'm taking a break from doing that optimization work because there's more important stuff that we can do first. So I should have done these in the other order around, but there are parameters that we can measure. So last week we had 48 unknowns. We had XYZ positions of all of the 6 base nodes and all of the 6 platform nodes, which is 36 unknowns. And then for each linear actuator, we don't know exactly how short or how long it is in its like most retracted state. And we also don't know exactly the mapping between revolutions of the motor spinning and linear movement of the actuator extending and retracting. And we should be able to measure both of these. So we should be able to measure the leg length mapping, so how many revolutions per millimeter extended or contracted. And we should also be able to measure the retracted length of the legs. And yes, this would simplify the optimization problem a lot. Nominally, it would get rid of a quarter of the unknowns, but I have a feeling that it would do more than 1/4 of the work of simplifying the optimization process, because the only ones that are left are just the position of all the nodes. And to me, that feels so much simpler than having to deal with the lengths of all of the legs and like these mappings and everything. Like adding those mappings in, I think would, yeah, massively complicate it. And as we saw last week, I was getting very not legit results from my very basic attempts at doing this optimization. So I think that by measuring these values, we can get a much better idea. And we have a much better chance of getting the optimization to work. Of course, I did consider doing this before, but I did not realize, I couldn't think of any way to actually measure these actuators because they're not terribly short. Like in their most, let me just grab one now. Like in their most compressed state, they're still quite long. And like, I don't have a ruler that's this long. My calipers certainly aren't. And it's not obvious to me how I can actually measure these things. So what I would want to be measuring is the distance from like this. I don't know if you can see, there's a ball in here, a magnetic ball. Well, actually it's a metal ball, but yeah, it sticks to the magnet on this side. I would want to be measuring the distance between that ball and this top part. And like that's pretty long. That's probably like 60 centimeters, maybe. I should probably know, but I actually don't. Like roughly what it is, but it's very long in any event. And yes, it wasn't obvious to me how to actually measure that. So I was racking my brain for a long time, like, how can I do this? How can I do this? I'm like, stuff it. I'm just not going to do it. I'm just going to add it as a parameter that the computer can optimize for. And that started the whole, I don't know, complicated business that we had last week. Cool. So we have a comment. So Hignaki says, I want curated videos, not a million no content live streams, unsubbing. Fair. Good luck on your project once it's done. I'm sure the argument will find me. Yes, I'm sure it will. That's fair. I can definitely appreciate this is not for everyone. And yes, so after last week, John and I were talking a little bit, and I realized that actually I have linear scales. We were talking about this process of measuring the legs like a while ago, and I bought some linear scales and then just completely forgot about them because I bought them, they arrived, I'm like, cool, I've got these, and then I put them in a spot in my room that I just can't see, and I just completely forgot that I have them. And because that was like 2.5, maybe 3 months ago, and it just completely left my mind. And oh man, like that, I wish I remembered last week, but unfortunately I didn't. But now I have remembered that I've got them. So I'm like, okay, cool. I can just measure the leg lengths directly. And so for reference, all of the scales that I've got, you'll see what they are in a sec. It's basically like a long ruler that can like digitally measure length. You'll see it in a sec. And so with these, I should be able to just measure the leg lengths directly. I can just put this linear scale against the leg, have some way of like lining it up with the points that I am caring about, and then that can measure the lengths. Also, I think. So I have, for the purposes of this project, I have 2 linear scales. One is 1 meter long, which is long enough to measure that pin-to-pin distance. So like from the ball all the way up to the end part that I just showed before. Taylor asks, what is the strength? I suppose hard to ask, what is the weakest length? Are you talking about for the linear actuators? Because for those, I've never actually pushed them. I've got a video on these linear actuators, and at the time I was using some weak string that had a breaking strength of only 7 kilos, and that was the weakest link by far. Like anytime I pushed the actuator to like be carrying a lot of weight, the string would break first. Since then, I've changed for this ultra high molecular weight polyethylene string, and this stuff has a breaking strength of like 100 kilos. So I'm pretty sure that's not going to be the weakest link anymore. But to be honest, I haven't actually pushed them to their breaking point since I've replaced this string. Because once I replaced that string, I'd already built all 6 actuators, and I do not want others. I don't want to deal with them anymore. It's very fiddly having to like thread the string through the actuators, and yeah, I didn't want to like, I don't know, go through that process anymore. So I haven't actually pushed them. So I'm actually not sure. I honestly don't really know what would break first. There's a lot, like, if you, in the description to this video, there's a link to an Onshape document, which has all of the CAD for the entirety of Juggabot, including the linear actuators. So you can check it out and see what you think yourself. But yeah, to be honest, I've got no idea what would break first. I'd love to know if you do any tests. I'm very curious, but yeah, I've got no idea. Yeah, no problem. Yes, so the 1 meter scale is long enough to measure the entire leg, which is like, oh, cool, great. And it measures to 1 micrometer precision. Fantastic. So we can know exactly how long the leg is to 1 micrometer, and we can know the mapping as well, of like revolutions to millimeters to 1 micrometer precision. Like, oh, so good. So good. Amazing. Easy. We also have, just as a backup, just in case the 1 meter one doesn't work, we have, it's actually 550 millimeters, is long enough, and that is long enough for the leg stroke itself. So we can measure like how extended or contracted the leg is, but we can't measure all the way down to that ball and all the way up to the top of the actuator. It's not long enough for that whole thing, but it is long enough for the stroke itself. And it measures to 5 micrometer precision, which is still pretty damn good. Again, yeah, it's not as ideal, but it should still work. So, yes, I started off Yeah, let's just keep going. We'll run into problems soon. So to start this this process of like figuring out how to actually use these linear scales, I started up with a very simple like serial communication over like to my Windows 10 PC, and that works really well. So like I have the Arduino code open here, and let me make it a bit bigger so you can hopefully read it all. And it's super simple. There's an encoder library written by the guy who makes the Teensy microcontrollers, and it's literally what 33 lines of code, and I can read from this linear slider. So as I move it around, you can see the value goes up and down, and it works nicely. And so this is the 550mm scale that's on here now. And actually, I can show you what this looks like here. So I've got it attached here where because this scale is not quite long enough to reach to the very top of the actuator, I've instead attached it onto the point onto like the bottom end of the actuator. And that should still allow us to measure the revolutions per millimeter because it's still moving with the end part of the actuator. So yeah, as I move that around, you can see the number. Well, the Arduino is like tracking that change. And I'm like, cool, okay, this is working fine, great. Now, I quickly encountered a problem with the 1 meter scale, which is that because it's measuring, as far as I'm aware, this is the problem, because it's measuring to 1 micrometer precision, as I move it around, it's spitting out a very fast rate of counts. So every time it moves 1 millimeter, there is a change in the signal. And I'll show you in a sec what that signal actually looks like. Maybe not in a second, in some minutes. But yeah, every time we pass 1 micrometer, we have a new signal of some sort. And that ends up spitting out lots and lots of data very quickly. Even when I'm moving the slider as slow as I can, still with using the Arduino is not fast enough to keep up with this just like torrent of data, and it ends up skipping counts. So if I move it really slowly all the way to the end and then really slowly back, it would be reading like 5 millimeters or something when it should be 0 or approximately 0. So it was definitely skipping counts. I'm like, like, damn it, why does it just not work? Because this would be so easy if it just worked. But I was like, stuff it, whatever, I'll just ignore the 1 meter one for now, and I'll just keep going with the 550mm one, because since that has a 5 micrometer precision, it's spitting out 5 times fewer like pulses for the same speed. So, and the Arduino can keep up with that. If I move it really fast, it can't, but as long as I move it slowly, it keeps up fine. All right, cool. Okay, we can at least use this for measuring the mapping of like revolutions per millimeter of all the legs. No problem. Also, I thought. And yes, so the serial communication works well with Windows 10, as we just saw. And there's no erroneous data. It's all there. It's all correct. It all looks fine. And I was like, oh, okay, cool. I can just go ahead with a 550mm scale, and I can just go with serial communication because it works. And then I can just connect that to my Linux PC, and this way, with my Linux PC, with the Juggabot computer, I can have the Juggabot computer control the leg to move through whatever sequence I want, while simultaneously reading the serial data from the linear scale, and then we can hopefully more easily align all of this data and then like compare the 2 data sets. In theory. James says, which Arduino are you using? The Teensy is meant to be much faster than the Atomigo-based ones. Indeed, and we'll get there. You're spoiling the journey, James. No, that's a very valid question. I'm using the Arduino Nano Every because a couple of years ago I bought like 10 of them, and I don't know, I like them. They're nice and small. It has a 16 megahertz clock rate, which should be fast enough because this should only be spitting out 1 megahertz signals. But I think the Arduino, you can't, as far as I'm aware, you can't like actually functionally reach that 16 megahertz for your own stuff because of like all the background processes that are running. They are nano indeed, yes. James says, yes, sounds like we've been down similar paths. Yes, I can't imagine this is a new problem, but it was fairly new for me, and it was very frustrating. Yes, so yes, it should work well with Linux, maybe, ... We'll see. Yes. Yeah, okay. So this begins my Tuesday serial misadventures. So, in order to get the Linux PC reading the serial data, first thing that you need to know is that your user on Linux needs to be part of the dial-out group. Otherwise, it doesn't have access to the serial ports. I'm like, okay, cool, I'll just add it to the dial-out group. That was a bit of a thing, but not too tricky. Something that is just driving me insane and took a long time to figure out what the issues here were is that between sessions, if I plug my Arduino into the Jetson, the Linux PC, then do whatever I want to do, finish, like, do my readings. If that, like, so I'm running all this in Python as well. If that Python session ends, like I kill it or the code finishes what it was doing, I can't just run that Python code again. The serial connection doesn't open. And I would think that this is because the serial connection is not being closed properly at the end, but I've gone to a fair bit of effort to try to make sure that that's closing properly. To be honest, I don't really fully understand exactly what I need to do in order to open and close that connection, but ChatGPT helped me out there, and it seems like it was the code that's there seems like it should be doing what it should be doing, but it's not working. So like if I try to run the Python code again, it just doesn't, like it connects fine, but there's just no data coming through at all. It just reads nothing. So I realized, okay, if I unplug the Arduino between sessions and then plug it back in, that works. I'm like, cool, okay, I can move forward. Easy peasy. Except for the fact that after between 3 to 5 plugs and unplugs, I've been keeping a tally and it varies from time to time. The port that I'm plugging the Arduino into, which is TTY ACM0, disappears. It goes away. I can plug and unplug the Arduino as many times as I like from this point on, and it's never going to connect. It's just gone. And oh my god, between these 3 problems, this was like just trying to figure out what was causing what to happen took so much time. It was like 6 hours at least that I was like between like, okay, time to, like, serial's working on my Windows 10 PC, time to get it working on the Jetson. Like literally like 6 hours later, I figured out that I needed to do this song and dance in order to get it to work. And this just about describes my feeling at the time. And yeah, the only thing that I've been able to figure out to fix this is to reboot the Jetson. Which is fine, I guess. Not ideal. And to be honest, in hindsight, after all this stuffing around, I should have just realized that serial communication is probably not the way to go here, and I should have just committed to doing something else, like, using the CAN bus that I've already got set up. But we'll talk about that in a sec. But I didn't. I was like, nah, stuff it. I'm going to get this serial to work because this is the easiest option. Like, I've already gone to this much effort, and I already know, like, now I know what the solutions are, so, like, you know, good old sunk cost. How much worse can it get? You know? Oh, yep, it continues. But I'll look at comments first. James says, don't worry, I'll get too frustrated. There's bound to be worse, more obscure issues that crop up. Yes, no doubt, no doubt. And Stormy says, I have a few Nano knockoffs and have similar issue with some machines, not all, failing to reinitialize my Arduinos between sessions. Thought it was just me. Haha, there you go. We're not alone. Yeah, I've got no idea. I can't help you. Like, I don't know why it happens. I just know that it happens. And yeah, it's a mystery. But yes, after all this stuffing around, at least it works, right? Right? Well, unfortunately not. Unfortunately, the serial data that is nice and clean on my Windows 10 PC is super noisy on the Jetson. So let me show you what this looks like here. I'll show you my pipeline that I've made to do this whole analysis process. Okay, where are we? So I've got this, I basically, to give you a quick little preface as to how we like get to this point, I have a sequence where the linear scale is attached the way that I just showed, where it's attached to the bottom of the leg. The leg will then home first to like set its reference 0 point. It will then stay there for 3 seconds. It then goes up to its most extreme point or thereabouts with like a little bit of, I don't want to get it to ram into the end accidentally, so I've got it like pretty much to the top. It will then sit there for 3 seconds. It then goes back down to home for 3 seconds, but it doesn't reset its 0 point then. It stays, like, the only time the 0 point resets is right at the very start. So it goes down, homes, again by like running through until the current spikes, like the whole kit and caboodle, except for resetting the 0 point. It then goes up to the top, waits for 3 seconds, and does this whole thing 5 times. So it goes up, down, 5 times. And that gives us the data that I'm about to show you now. So the first thing that we have is super noisy data. And so you can hopefully see all of these points here are the data that's collected from the serial port. And this, when the serial port is printing, it's just printing the position. So it'll be like, I don't know, 10.005 or whatever. And that's in millimeters. And you can see here, there's a bunch of red points and a bunch of green points. And because this data is so damn noisy, ChatGPT helped me make this like interactive, what is it called? Sliding window. That's not the proper word. They like a moving average. That's the one. A moving average filter, so that I can easily filter out, or somewhat easily filter out, all of the outlier data. I don't know. I just kind of took it as like given that this data is going to be noisy. So I'm like, all right, cool. Let's just figure out some way to filter it out. Manually tuning this like window size, which is like how many neighboring data points are we considering, as well as the threshold factor, which is like, yeah, basically the way that this filter works is we take some number of points, the window size. So right now we take 4 points, like consecutive points. We then say the next point is probably going to be pretty close to where these past 4 were. And we're going to allow it to be within some threshold of where the average of those 4 points is. So as we have a bigger window, we're averaging over more points, which means we'll remove outliers more easily, but it means that we're going to be missing areas where the data changes really quickly. Because if the data actually does change really quickly, it's not going to match up with the average from before, because that average was like flat, for example. And yeah, tuning these values manually was very tedious. So I'm using this script to basically like go through and find a window size and a threshold factor that works nicely. And I ended up picking, I think it was 12 for window size and 0.99 for my threshold. So I'm not gonna be able to get it exact, but it was like this. And it was a little bit like, maybe we can try to get close. Yeah, it was pretty much this, except without like this point here. And like, yeah, it's much better. It definitely gets rid of pretty much all of his outliers. I'm like, cool, okay, we can progress now. We've gotten rid of the outliers. We have gotten rid of some actual data, like in here, like this is just gone, but we have 5 rounds, so it should be fine. Maybe. So then we take that filtered data and we can plot it against the measured data from the motor. And now the immediate thought that comes to mind is like, whoa, hang on, like why are these scaled so differently? But it should be this way because the blue line, which is the motor position, is measured in revolutions, while the red data is measured in millimeters. And this is exactly that mapping that we're trying to figure out. But you'll note that the 0 points of this data they're way off. They're not even aligned remotely. So the next step is to align these. And this is where the fact that I've had it sit at 0 for 3 seconds is very helpful, because these are just sitting there, nothing is happening, and so we can very easily take the average of the first 2 seconds, let's say, and then make them so that they're 0. And even though this one looks like it's 0, it's not actually, it's just off of, oops, it's very, very slightly off. Yeah, so the next step is to align the data, and that's what we get here. So the scales are still way wrong, but at least we are in agreement about where 0 is, which is very nice. And then the final step, well, maybe not the final, the next step is to actually scale this. And this plot right here is a very crude way of scaling the data, which basically takes the minimum of the data and the maximum and then makes them the same. So whatever the minimum and the maximum were for the motor positions, we look at that and we say, okay, whatever the minimum and the maximum is for the measured data, we just take them and then we scale them so that they are identical. And this right now we have scaled the motor position so that it is now in millimeters as well. So all of this is in millimeters. And like that looks pretty good, right? Like they seem to line up nicely, especially when you zoomed out this much. But to be honest, like, it is actually, it's pretty close. But how close is it? Well, that's where the last plot comes in, which is showing our error. And I don't really know why this error, like why this bottom plot is so discontinuous, but this is showing the error in millimeters between the two data sets. And we can see that when we are at the very top or at the very bottom, the error is pretty small. Like, what are we looking at here? Less than 0.2 millimeters. Like that seems pretty good as far as I'm concerned. But once we move into like the zone where it's actually moving, our error goes up quite a lot, up to like, what, almost 6 millimeters, which is a problem. 6 millimeters of length, I don't know for sure, but I'm willing to bet that 6 millimeters difference between where the leg is and where the leg is supposed to be is gonna cause problems. But I don't know if the error is actually 6 millimeters, because if we look very closely, we can see that these data points are not perfectly aligned horizontally. So it's kind of tricky to see, and I need to get better at the way that this zooms. And I think this is a bit of a bad example, but I think that what's happening is the time stamping. So let me, to explain what I think is happening, I need to explain how I'm actually collecting this data. The motor position data is being read over the CAN bus, the same as it is when Juggabot's actually in operation. And that's happening at, I believe, 100 Hertz. So we have 100 Hertz of exactly where the motor is measured to be. And then for the serial data, because I can't print the serial data that quickly because it slows down the Arduino and then makes it miss counts, which is another red flag that I shouldn't be using serial, but whatever. That's only printing out at 20 Hertz. So the serial data is a bit behind, and of course they are going to be slightly out of sync. So when I'm recording these, I have two like separate threads. Like there's one for the motor position data and a thread for the measured linear scale data. And then as soon as a new data point comes in, we read that data, we slap a timestamp on it for when we received it, and then we save it. And then we just keep running both of these. And so they're kind of running like asymmetrically. So like the 100 Hertz one is obviously running 5 times faster, but not all of these timestamps are going to match up perfectly. And it's possible that they actually might be slightly out of sync, especially because serials are a bit crap. So what I think is happening to describe most of this error is that these data are not actually lining up perfectly. And also, so it may look like it's actually pretty close, but like here we can see that it's possible that this is shifted up or down, which would be the error that we're actually trying to get rid of, or it's possible that it's shifted side to side, which is something that I'm not really that worried about in actual operation because there's going to be no second data set that can be out of sync. So it's not, it's tricky to distinguish the way that this curve has been shifted. And also it's worth keeping in mind that these two, I've already shifted the measured data by like 0.12 seconds, I think. So I've already shifted it by some small amount to try to make these line up a bit better. And I just like found that value manually. I was just experimenting with different offsets until it seemed to line up nicely. But it's weird that like on the down stroke, it's not lining up very nicely at all. But then on the upstroke, it is. So yeah, I'm not fully convinced that what I think is the problem is actually the problem. I just think it might be. Yeah. So overall, like it looks decent. It's pretty close. And actually, there's one other thing that I want to show before moving off these plots, which is that the reason why I've got it to go up and down 5 times, or one of the reasons why, is that I wanted to see how repeatable this homing sequence is. Because as a reminder, the way that the homing sequence works is that the leg retracts and retracts and retracts until it hits the foam end stop. And once it hits that end stop, the current in the motor spikes, and the O drive detects that spike in current and then realizes, okay, we are probably at the end stop, or we've hit something else, but there's nothing else to hit, so we must be at the end stop. And I wanted to see how repeatable this is. Because it is just running into like a little foam pad, it's like, maybe the foam is getting more compressed over time. I don't think this 5 examples would really pick that up, but like, it's just foam. Like it's not, I don't know, it doesn't feel as repeatable as it could potentially otherwise be. So I wanted to see how repeatable it actually is. And yeah, that's why it's helpful that it has done this 5 times. And if we zoom in to just this section, We can see that it's not quite perfect. They are definitely deviating, but not by a huge amount. So keep in mind this is millimeters on the y-axis, and yeah, we can see that. Let me get rid of me, so you can see the whole thing. All of these red lines, so like the measured data is, yeah, within 0.15 millimeters, and that feels pretty good to me. I'm not super concerned about that, like for now at least. Especially because it is possible, even though with this shorter scale, as far as I'm aware, I can slide it up and down and it will get pretty damn close to 0. I don't think it goes straight back to 0 because I think that the Arduino still does miss some of those counts. So these homing positions being as close as they are, I feel pretty happy with this for now, given the setup. It's hard to know if this is caused by the homing actually being in a different position, or if it's because the linear scale is missing counts. Because the Arduino is not fast enough. Yeah. And it's a similar sort of deal at the top. The tops don't quite match up, but they don't match up in like a different way. It's like not... I would have thought that like maybe we would have like, I don't know, if like here, for example, we've got one that's higher than the neighboring ones, maybe then the homing sequence for the next one will be higher as well, but that's not how it has turned out. Yeah, so we can see these are also within, I don't know, what is that? Same sort of thing, 0.15 millimeters. So pretty damn close, but not perfect. Okay, let's see. Biohazard Madness says, hey, how's progress going? It's going good. We're getting there. It's a process. We're getting there though. Stormy says, when it's not moving, the error is low, means there might be some slight slippage or just the motor steps affecting the motion sensing. Possible. James says, the error appears to be the movement lagging the command below the command position when moving up and above when moving down. Friction momentum thermodynamics, potentially. That is actually, that's a very good point, James. I'm glad you mentioned that, because in this data, I'm actually not showing the commanded position. And you are right that I probably should be recording that as well. Oh, yeah, I'll record it as well, and that way like I'll have that data in future runs. But for now, so the blue data is the measured position of the motor from the O drive, and the red data is the measured position of the linear slider from the Arduino. So both of these are measured, and yeah, they should be lining up perfectly. But yeah, as you can see, they're not quite perfect. Yeah. All right. So yes, the serial data is very noisy, and initially I kind of ummed and ahed about how to deal with this noisy data for a little while, and one of the I'll show you this. Yeah, one of the approaches that I don't know. I figured I would toy with the idea, and yes, so actually, why is my mouse not working? What did I do? Alright. Yeah, so you can see here, this is the full plot of like all the noise, and like, yeah, there's a lot of noise. But yeah, one thing that I was considering doing as a way to filter out this noisy data before I had that like dynamic thing where I can automatically, like I can just change the slider, change the window size and the threshold and that sort of stuff. Before I had that, I'm like, maybe I can just go into the CSV and just manually delete the rows of data that are outliers. And I can just see them. I can say, yep, that data is an outlier. I'm going to get rid of that. I know this is obviously not a very future-proofed idea, but I figured I'll time myself, see how long it takes. I only need to do it 6 times, maybe, like once for each leg. So if it's only like 5 minutes, how bad can that be? And in the process of filtering out this data, let me zoom this in a bit more so you can hopefully see it. So this is our... How do I zoom in on this? Yeah. This is all of our raw data. So we've got the timestamps for the motors, timestamps for the Arduino in Unix time, the motor position as measured by the O drive, and then the Arduino position from the linear slider. So I was going through, I'm like, okay, cool, like these all seem fine, like they all kind of line up. I'm like, okay, 995, that's no good. That's obviously no good. But something that was not obvious from the outlier serial data, that is very obvious when you look at this, you say, hang on, this is 53995, these are all 53995. This is 53995, but it's been sent as 2 messages instead of 1. That's interesting. Let's see, what other ones we've got? For some reason, there's just a blank one with nothing in it. That's cool, all right. This one dropped its negative. Cool, cool, cool. We can keep going through. There's a couple other erroneous ones in here, but we can see there's quite a few times where the data is getting split over 2 messages. 240028, 24028. And same thing here, 24028. This one gets split up into 2 and 40.28. And of course, both of these data points are now going to be outliers when we plot them the way that I had plotted them before. Yet another red flag of using serial communication. So it seems like what's happening is that the serial data that is being sent over, I guess maybe the Arduino IDE on Windows 10 seems to handle, maybe it just handles these misfires a bit better and can like get rid of them and just it doesn't plot them or something. I don't know what's going on there, like why it works perfectly with my Windows 10 PC, but as soon as I plug it into the Jetson, we're getting this like random like splits of the data. Not exactly sure why it's happening, but I just know that it is happening and it's reliably happening and I don't want it to happen. So yes, serial is no good. Biohazard Madness says, well, there's a saying with engineering, it's not a walk in the park, it's more like a drunken stumble up a steep rocky hill. Honestly, that is a pretty fair descriptor of how I have felt a lot fairly recently. It's just like rambling around trying to find something that works. But thankfully, after yesterday, I've got a clear goal in mind. At least I've like locked onto the next tree up the hill, let's say. And I can at least get myself there. So that's good at least. Yeah, so after all this, I'm like, well, serial's clearly not the way to go. Let's ditch that. And while we're at it, like if we're going to change over to the CAN bus, well, actually, that was a bit of a spoiler. So yeah, my thought was like, okay, if I'm getting rid of the serial, then what can I do instead? Well, the Jetson itself does have GPIO ports, so I could just hook it straight onto the GPIO ports of the Jetson and go straight from linear slider to Jetson and just like skip out the microcontroller entirely. Maybe that would work. I had a bit of looking into the Jetson's speed of like its clock speed and whether or not it would be able to keep up with this linear slider. That didn't seem super promising to me, and I haven't done anything on the Jetson with the GPIO ports before, so I'm like, I don't know, not super eager on that. But then I realized I have the CAN bus right there. It's all connected up. I could just tap into that CAN bus and then send the data over the CAN bus. That should be pretty good. But the Arduino can't connect to the CAN bus, so I can't use the Arduino for this. But I do have one extra teensy on the floor. I have one more teensy lying around, so I could use this, and I've since bought more because it turns out these are pretty damn useful microcontrollers. And the teensy, this is the same thing. I've already got one of these connected to the CAN bus, so I know that I can connect this. I've already got all of everything that I need in order to connect this to the CAN bus. So I'm like, cool, I can use the teensy. And as someone mentioned before, the teensy has a much, much, much faster clock speed, and so it should just like if I used the exact same code that I was using on my on the Arduino on the teensy, it should work, no problems at all, even with the longer scale with the more fine resolution. But even better than that, the Arduino actually has inbuilt into it four decoders for quadrature signals, which I'll explain what these actually are. Actually, no, I can explain them now. So, So this, the linear slider outputs, it's called a quadrature encoder, a quadrature signal. So you'll have two signals, like A might go like this, and these should be perfect, nice, stepping, like a nice square wave. Nope, that's not what I wanted. Okay. Oh no. Okay, I'll just do it in red as well. And B, and these signals will be offset from each other. So let's say the B starts up, it will then go down, and it's like 90 degrees out of phase. So when it moves, like let's say for the longer slider, it will move by 1 micrometer, then we'll have one of these two signals will change. We move another micrometer, and the next one changes. We move another micrometer, and the next one changes. And by looking at both of these signals, we can see exactly how far the slider has moved, since each of these step changes indicates a movement of 1 micrometer. And we can also see what direction it's moving in based on like, okay, B has triggered from up to down, and A, then the next one, A triggers from down to up. That means we must be going in one direction. Versus if it's the other direction, you're going to see the inverse of that ordering. And yes, so that's how this data is being sent across. And the Teensy has 4 encoders in it that are like hardware encoders that are specifically made to read this data extremely quickly. I've seen some, I was looking through some forum threads and people were getting it up to like more than, I think 10 megahertz, which is like 10 times more than what I need for this. So I'm like, awesome, cool, we're good. We can use the Teensy to connect to the CAN bus, and then we can read the linear slider data and yeah, read that with the quadrature encoder on here, convert that into like millimeters, and then send it over the CAN bus, and we should be good to go. Except for the fact that the linear sliders work on 5 volts, and the Arduino, the Teensy can only support 3.3 volts on its like input pins. So we need to change the 5 volts from the linear slider down to 3.3 volts for the Teensy. And this is where we start wondering if we can use the 1 meter slider after all. So there are some problems with it. The problems are that it has, what have we got? Yes, signals are 5 volt. I've done this in the reverse order. So signals of 5 volt is one problem. Another problem is that there's a very fast data rate, so 10 to the 6 counts per second. But as we just talked about, the Teensy should be very capable of keeping up with that. But the one that I haven't spoken about yet is that we have a very messy signal. So while we should be getting this nice, perfect, crisp, clean square waves, what we're actually getting is not like that at all. And if I can find my window... Oh my goodness, I've got so many things open. Okay. Yes, here we can see my oscilloscope. So I will get rid of my thing. And as I move this, oh, let me just turn the power on. Cool, so this is hooked up to the A and the B channels. I don't remember which one's which. The yellow, let's say the yellow one's A and the purple one's B. Doesn't really matter. But as we move this around, it's like, okay, cool, it's kind of hard to see what's going on. But we can set up a trigger so that as I move this, we can stop that there. And like, look at that. Like that's not the nice, crisp, clean square waves that I drew before. For some reason, there's some kind of weird like coupling between these two signal lines. And whenever one changes, it also affects the other one. So yeah, you can see there's like kind of like a double stepping kind of situation going on. Very weird, not ideal. It's possible that like this is potentially square wavy enough that it wouldn't be an issue, but I don't think that that's the case. I think that this is problematic enough that it will cause issues. Because as far as I'm aware, these quadrature encoders, what they're looking for is a rise or a fall of like the line that they're measuring. And if we are only looking at rises and falls, then if we're using this data here, we have, like for the yellow one, we've got a rise here and then another rise here straight afterwards, even though that shouldn't be there. That's like a false rise. So we should only have rise and then the fall down over here. So this is problematic. Yes, but after a lot of looking around, I've realized that it should be possible to work through this. We can first use what's called a Schmidt trigger to clean up the signal. And what this looks like is like this. This is from Wikipedia, which has a fantastic article on Schmidt triggers. And the general idea here is that A is if you're only looking at a certain threshold point. So if we have this like brown threshold line, and anytime our data is above that line, we say that it's high. Anytime the data is below the line, we say that it's low. Then we get these weird things like this, where when the data just like bounces back and forth over that line, we get erroneous like high-low changes. And of course, this isn't exactly how the quadrature encoding that I'm using would work. It would instead see like this down step as a down, and then the corresponding up as an up, and it would get even more confused than what this A is showing here. But what the Schmidt trigger does is rather than just having a single threshold point where we say anything above is high, anything below is low, we have two thresholds. And we say for the high one, anything above that is high, and for the low one, anything below that is low, but anything in between is nothing. It just stays as whatever it was before. And what this means is we get this output here for B. So once the signal goes above, if I can erase, once the signal goes above the upper threshold, it stays there until it goes below the lower threshold. And then it stays there until it goes above the upper threshold. And this way, if we have this data here, actually what we can do is, take a screenshot, chuck it into, oh, I can't just paste in here, can I? Okay. Damn it. That was so close to being so good. And I don't want to exit my PowerPoint. But yeah, if you imagine that same trigger being applied on here, if we have a threshold like here, if we set these two thresholds properly, then all of these like half little steps are just going to be ignored because it's still above the threshold, it's still above the upper threshold, and it's still not below the lower threshold, so it should be nice and crisp and clean. I say should because I haven't actually set this up yet, but we'll see. And yes, to do this, I have purchased, for all of these chips, I've gotten 2 of them in case I break one, but I've got this Hex Schmidt trigger inverter, which was only $1.30. Very nice. Oh no, $1.45. And then, so that solves that should at least solve the messy data signal, the messy data problem, and we'll have nice clean square waves. And then it's still at 5 volts, and so we need to now convert it down to 3.3 volts. So I've bought a logic level shifter to do this, and I bought this hex buffer integrated circuit with an open collector output, which I've been learning all about from yesterday. And essentially what these are is they will take in a signal, and normally by default it will not do anything with that signal. It'll just take it in and then nothing happens with it. But if you tie a pull-up resistor to the output pin to whatever voltage you want, it will then output your, like, it will just basically take your input data and then output the exact same data but scaled to be proportional to whatever your voltage is that you're pulling up that output pin to. So for me, I can input a 5 volt, hopefully nice, clean, crisp square wave, and then I can tie the output pin to 3.3 volts, and then it should scale that input to 3.3 volts, in theory. ChatGPT assures me that this is going to work. And I think it should as well after my separate reading about how these things work. But this is the idea. So I'll have, so each of these are both, they say hex, and this confused me a lot initially, but it turns out hex just means that there are 6 of these Schmidt triggers on this board. So like each pair of pins is 1, and then there's like ground and power. And then the same thing here, we've got a hex buffer, which means that you can do this 6 times. Yeah. But yeah, I'm pretty sure this should work. Unfortunately, I haven't had time to actually wire all this up yet because I only got these yesterday. I made it like 4 minutes before JCar closed, which was so lucky. But yeah, thankfully I have them now and I should be able to, yeah, that'll be my day today, is getting all this wired up. I've copied the same slide again. And yes, will it work? I hope so. I definitely hope so. Because if this does work, then this means we can use the 1 meter scale and we can just measure the full length of the whole actuator. And we will know within 1 micrometer precision exactly the length of the leg in its shortest position and the exact mapping of like millimeters to revolution for every single leg. My plan is to do this for each leg individually, and then we will know all of these values for all the legs perfectly. It's the dream. And until this happens, I can't put Jugglebot back together again because I don't want to be moving this, basically for this like measuring rig to work, the platform can't be on top. I have to do the legs individually by themselves. So I have to go through this whole process before I can even put Jugglebot back together again. So I'm, yeah, definitely very motivated to get this working. Yes, and that just about catches you up. There are a couple little things as well that have been going on the side, but I think I'll wait until those are at a more complete state. But yes, definitely super, super frustrating week at times. But I am very relieved that I now have these chips, and I think that they should work. Big fingers crossed, because this was a yeah, a very frustrating process to figure out. Yep. But we're getting there. And yeah, so the plan is that like once I have this mapping for all of the legs, I'm gonna just like triple check that they're all correct, because I don't want to have to take the platform apart again to do this again later on if it turns out this mapping is wrong. So I'm gonna go to a lot of effort to make sure this mapping is as correct as possible for all the legs, and then once I feel good that it is, put the platform on, and then first thing I want to do is just move the platform around, go through its try to draw out a smiley face, and just like see how bad it is, how far away the platform is from where it's supposed to be, because I have a feeling it's going to be a lot better. Out of all of the 48 unknowns that we had before, I feel pretty strong that these 12 related to the legs, like the shortest lengths and the mapping, I feel pretty good that those 12 are the largest sources of error. I don't think that the position of the nodes on the platform or the base, I don't think they're going to be more than like a millimeter or two off. Yeah, we'll see. And actually, I want to quickly give a shout out as well to Albert on Zulip, who has offered to have a look at the optimization problem. And he has some experience with optimization, looks like for tensegrity structures, which is pretty cool. And yeah, so thanks, Albert. It's very, very, very kind of you. I'm very keen to see where this goes. Of course, I'm not going to have any like proper data to optimize with until I've gone through this process of figuring out the leg lengths. So it's probably going to be a week or two before we can actually start this optimization process in full stead. But we'll get there. We'll get there. Cool. All right. Well, I hope you found this interesting, and yeah, go through all the comments. Yeah, I hope you found this interesting, and I will see you next week. Until then, have a good one, and good luck with everything you're doing.